So this is mostly still in the spinal cord. Just a touch of brainstem whenever we bring up the parasympathetic preganglionic neurons. We'll hit them again whenever we talk about the cranial nerves that they form. But they will be mentioned today because today's all about the autonomic nervous system. You probably don't give it much thought.
Jokes.
That was unintentional. I'm going to use that next year. But you should. You should give it thought because it does a whole lot for us. Some of it we'll be talking about in later lectures whenever we talk about the barrel reflex. But this helps kind of maintain homeostasis for us with our viscera, with our non-skeletal muscle. And skeletal muscle is great and all, but it's certainly not the only thing that's helping our body work. And so those other non-skeletal muscles, those are going to be innervated by autonomic fibers, which we don't have exquisite control over. Those are going to be governed more by sensory input from the body, whether there's a change in blood pressure due to a change in how gravity is affecting your body. Maybe you hang upside down or lay down or stand up quickly. The autonomic nervous system is going to sense that and respond. Noxious stimuli are also going to stimulate your autonomic nervous system. It'll create a sympathetic response, a stress response, so you can do something about that noxious stimulus. Usually there's some kind of pain bringing that on. When we don't have proper regulation of our autonomic reflexes, then that noxious stimulation creates a problem. That'd be your autonomic dysreflexia. But that'll be the second part of the lecture. First, we're just going to distinguish between our sympathetic and parasympathetic branches. Fight or flight, rest and digest. If you got that, that's a pretty good start. Now, how they do that, well, that's not very complicated either. They release different neurotransmitters that act on different receptors, and we'll touch on some of those. Specifically for the heart, the GI tract. We'll also touch on the bladder and the genitals. Gently, of course. Glad you made it. Okay. So we're starting in the central nervous system, almost always in the spinal cord, but not quite. The parasympathetic preganglionic neurons are also in the brainstem. We'll start off with the sympathetic neurons, though. So sandwiched in between our parasympathetic preganglionic neurons, we have the sympathetic preganglionic neurons. And in both branches, we're really just dealing with two neurons. There's the preganglionic neuron, which is before the ganglion, and then the postganglionic neuron, which arises from that ganglion or collection of cell bodies in the peripheral nervous system. That's all a ganglion is. If it's in the central nervous system, we call it a nucleus. Outside, we call it a ganglion. But it's just a collection of cell bodies. Those cell bodies are then going to innervate target organs. So here's our target organs right here. You'll notice skeletal muscle is absent. Here we're dealing with glands. We're dealing with smooth muscle, cardiac muscle. The sympathetic nervous system is going to arise from the thoracic and upper lumbar regions of the spinal cord and those lateral horns. They're then going to innervate the postganglionic neurons, most of which are in the sympathetic chain ganglion right here, or the paravertebral ganglia. So there's a pair of these on both sides of the spinal cord, just one here in this cartoon. Some neurons will ascend and go higher than their spinal level to hit the cervical and stellate ganglia and innervate the head. Others will descend and head to this lower lumbar and sacral region so they can innervate the lower limbs. Many of them will just head on over, staying at their same level, and innervate the sympathetic chain ganglia here. And then others are going to pass on through and hit the unpaired prevertebral ganglia that are scattered away from the spinal cord. These are going to innervate the GI tract and the genitourinary system. Some will also pass through and directly innervate the adrenal gland, which has a small subset of postganglionic. sympathetic neurons. Just two neurons. The preganglionic neuron is always in the spinal cord. Postganglionic is usually in this sympathetic chain ganglion here, but they can be elsewhere. They can be scattered in these prevertebral ganglia as well. As you can see here, a lot of what they're doing is priming us for activity. So opening up our airways. This way we get better gas exchange. We need that if we're going to generate ATP and actually power movements. Increase heart rate. Move that now well-oxygenated blood throughout the body. Again, priming us for activity. The sweat is a little weird because these release acetylcholine. We will stimulate some sweating there. We're going to slow digestion. Now is not the time. This is not rest and digest. So the beta adrenergic receptors on the GI tract are going to slow peristalsis and slow down digestion. We'll inhibit salivation. Again, this is not the time to eat. What's going on down here, we'll touch a little bit later, but essentially parasympathetic will be point, sympathetic will be shoot. We'll get to that. The other side of the coin would be the parasympathetic branch over here, which has the opposite effect on all of these same target organs. So now it's rest and digest. We'll have a little salivation. We're going to stimulate peristalsis. We'll move blood into the gut. The parasympathetic nervous system is all about sort of energy storage, working with the food that's in front of you. So we're going to have some pupillary constriction so we can focus on closer objects as opposed to the dilation that we get with sympathetic innervation, presumably so we can let in more light and see further objects. The bulk of the preganglionic neurons are going to be found up in the brainstem, and they're going to form cranial nerves 3, 7, 9, and 10. These will innervate different parts of the head. We'll innervate the eyes to control the size of the pupils, the thickness of the lens. We'll touch on our accommodation of pupillary light reflexes later on when we talk about innervation of the eyes. There'll also be some moisturizing of the eyes via the facial nerve. We'll moisturize our eyes, nose, mouth. Glossopharyngeal nerve is also going to help with that salivation, moisturizing the mouth, so priming us for resting and having a meal. The bulk of our viscera are going to be innervated by cranial nerve 10, the vagus nerve. And then we have this sacral region down here of preganglionic neurons that are going to innervate the genitourinary system as well as the rectal ganglia, so to control defecation. There are some similarities between both of these branches. So the preganglionic neurons are all going to be found in the central nervous system. They have that in common. Many of them are in the spinal cord, except for those that are in the brainstem. They all release acetylcholine, and they're all going to act on nicotinic acetylcholine receptors. The postganglionic neurons are a little different. They release different neurotransmitters, with the exception of those sympathetic neurons that innervate sweat glands. They release acetylcholine, but everything else releases norepinephrine or noradrenaline. The sympathetic ganglia are found typically close to the spinal cord, whereas the parasympathetic ganglia are found on or very close to target tissues. So sympathetic is going to be close, parasympathetic far away, in relation to the spinal cord, that is. The synapses that our postganglionic neurons form are kind of like those neuromuscular junctions. These are called neuroeffector junctions. And with this, the axon runs along the target tissue and creates a number of what they call en passant synapses, where they just, as they're passing along, form synapses. So they'll create multiple synapses along a single axon, innervating that target tissue. So there's multiple sites of release, multiple sites to detect that release, and so you get a more pronounced effect on your target tissue. And this should make sense. We're not processing any information. We're in the peripheral nervous system. The decision has already been made to stimulate this tissue. We're not putting this to a vote. we're creating a pronounced effect here so we get the effect that we want, whether it be relaxation, excitation. It depends on the target tissue and the neurotransmitter that we release, but we're going to get a pronounced response because we have many synapses formed by each neuron. So there's no voting here. When the postganglionic neuron is excited, it then stimulates whatever effect it's going to stimulate. And that depends on what we're talking about. So for the sympathetic nervous system, where we're releasing norepinephrine, we're going to stimulate adrenergic receptors. And different adrenergic receptors have different coupling. Beta, we should be thinking GS. Alpha 1, GQ, alpha 2, GI. We should have these floating around in here, or at least on our note sheet. And we should know what those G proteins do for us. We're going to add a little bit of a wrinkle because we're talking about smooth muscle now. And GS doesn't stimulate smooth muscle, it causes it to contract. So it's a little different there. You got to keep that in mind. In the heart though, beta, which is GS coupled, this is going to be excitatory. We'll go over why it's excitatory. It's excitatory at a few different locations. There's a little bit of inhibition going on, but it's all for the best. But in general, when we're thinking heart and beta adrenergic receptors, we're thinking activity. Increased rate of pacemaking, stronger contraction, better blood flow to the heart. So whenever you apply beta adrenergic agonists, here's two of them here, and you look at the heart rate, 0 being where it started, not actually 0. You can see an increase in the heart rate with the additional administration of these agonists. So on the X here, we're just seeing the number of administrations, and on the Y, the increase in heart rate. Increase the dose, increase the heart rate. That should make good sense. These are GS coupled. These are going to increase cyclic AMP levels. That'll lead to depolarization. We'll talk about how in just a bit. That's going to be faster pacemaking. In the GI tract, it's a little different. Same receptors on the actual GI tract itself, on that smooth muscle. Because it's smooth muscle, it's going to relax. The interaction between actin and myosin and smooth muscle is governed by the phosphorylation state of the myosin head. We need to have myosin light chain kinase active in order to phosphorylate the myosin light chain and allow it to bind to actin. The activation of protein kinase A by our beta adrenergic receptors inhibits myosin light chain kinase. No more interaction, no more contraction, thus we get relaxation of smooth muscle. So smooth muscle is the exception, and here's why. We'll see a little cartoon of this later on to remind you of that, because this is tricky. GS is supposed to be excitatory, and it is, except in smooth muscle. There are also adrenergic receptors, but these are going to be on the parasympathetic terminals. Alpha 2, GI, yeah.
So are they're still GS coupled,
Yes.
but they're just inhibiting now? Or
Yes.
okay.
Yes, because the interaction between actin and myosin is not governed by calcium levels in smooth muscle. Instead, it's whether or not myosin has been phosphorylated. So it depends on the activity of different kinases and phosphatases within the cell. If we bias the cell toward having myosin light chain phosphatase active, which is what happens here, and we inhibit this kinase, then we dephosphorylate myosin, no more actin-myosin binding. If they don't interact, you can't contract. So smooth muscles are a little different. And when you look at their contractions, they're very, very slow. And that's because they're not governed by fast calcium dynamics like skeletal muscle. Yeah.
But we're not changing the inherent ability of GS. It's still activating.
It's still stimulating adenylyl cyclase, yeah, but it's not exciting the target tissue. But GS still does exactly what it does in every other cell. It's going to stimulate adenylyl cyclase, it's going to increase cyclic AMP levels, and that's going to activate protein kinase A. From there, the devil's in the details. Here's the detail that matters with smooth muscle. Protein kinase A inhibits myosin light chain kinase. If If we don't phosphorylate myosin, it doesn't interact with actin. If myosin doesn't interact with actin, we can't contract. Smooth muscle contractions, you'll see they're very slow, as opposed to skeletal muscle, very fast, and that's because they're governed by very slow processes, like phosphorylation and dephosphorylation. The adrenergic receptors are inhibitory, so this all makes good sense. Whenever we have sympathetic input to the GI tract, part of the reason why digestion slows is because of inhibition of parasympathetic fibers. Those parasympathetic fibers have alpha 2 adrenergic receptors. They're GI coupled. That's going to cause them to hyperpolarize. It's going to decrease neurotransmitter release, so we're going to decrease the amount of acetylcholine that's being released onto the GI tract, while at the same time dumping out norepinephrine to activate protein kinase A and cause relaxation. Here we can see the application of an alpha-2 adrenergic agonist onto an isolated pig ileum. So we're looking at small intestine activity here. 100% would be whenever they didn't have any drug added. What was the peristaltic flow? That's what we're looking at here. Circular and longitudinal contraction, so squeezing and shortening, yeah.
So are both of these happening at the same time?
Yes.
Okay.
Yes. And so this also helps give you a more pronounced effect. So you're applying the gas and letting off the brake, or vice versa. So in this case, we're putting on the brake and we're removing the gas. So here's our brake, and here's taking off the gas. So we're no longer releasing acetylcholine, well, we're reducing the amount of acetylcholine released from our parasympathetic terminal. And when you do that, you can see a decrease in the overall flow through this pig ileum because of a decrease in circular and longitudinal muscle contractions. So increase the dose of the alpha-2 adrenergic agonist. In real life, it would of course be norepinephrine, but in this case, it's clonidine. Decrease GI activity. So we can act directly on the target tissue, or we can act on the terminals. For the parasympathetic nervous system, it's the opposite. So rest and digest. So in the heart, we're relaxing. We're decreasing pacemaking. That's primarily where our parasympathetic input is going to act. It's really just at that sinoatrial node. The receptors there would be M2 muscarinic acetylcholine receptors. The important point is that they're GI coupled. Decreased cyclic AMP levels, that's going to slow pacemaking and decrease heart rate. So when you antagonize muscarinic acetylcholine receptors with atropine, here's baseline and then increasing additional doses of atropine, you can see the heart rate increase. So when we antagonize this, we don't slow, instead we then speed up, because we're decreasing, we're letting off the brake essentially. In the GI tract, totally different. We have different muscarinic receptors. It's the same neurotransmitter, but we're acting on M3 muscarinic acetylcholine receptors, and they're not GI, they're GQ. They have to be GQ if they're going to stimulate smooth muscle. GQ is going to lead to the activation of myosin light chain kinase. So we're going to phosphorylate myosin, we're going to allow actin myosin interactions in smooth muscle, and we're going to facilitate contraction. This is that digest portion, rest and digest. What we're looking at here is just the makeup of different muscarinic receptors. So they've done a few different knockouts. They're looking at the bladder in A and B in males and females, and they're looking in the small intestine in males and females down here. These would be mice, of course, not people, because what they've done is generate either M2, M3, or M2 and M3 knockouts. And what we can see here is that our small intestine down here, the biggest effect that we see on our muscarinic agonist comes whenever we knock out M3 receptors, so down here. Primarily, we're looking at M3 muscarinic acetylcholine receptors. Here's where M3 is intact. We still have a pronounced effect of drug, not so much down here, whether you're male or female. So based on which muscarinic receptor you have, and more importantly, which G protein lies under the hood, that's what's going to determine the effect of these different branches of the autonomic nervous system. So you might want to have a little table where you have the receptor and then whether it's GS, GI, GQ. And just remember, smooth muscle is a little different, where GS is going to actually inhibit it. Now, the autonomic nervous system is not just output, there's also input. This is what allows it to create the reflexes that we'll be covering in the next portion of this talk. But it also allows them to have some sense of what's going on in your viscera. Is there any irritation? Have you ever had a tummy ache? Yeah, me too. You can't really pinpoint it. It's sort of diffuse. My tummy hurts somewhere in here. When you have a cut, it's very easy to localize. I have a cut right here, not in this general area. I think there's a cut. And that has to do with the widespread innervation of our viscera. We don't really have any two-point discrimination like we do out there in our skin, where the sensory nerves cover a very small area so that we can distinguish different parts of the finger. We don't really need to do that with our GI tract. We're not laying that out and feeling the world with that. If there's any pain anywhere in it, it's all the same. There's something wrong. So we get this sort of diffuse visceral pain whenever we have irritation. Usually this is due to introducing some foreign invader and you get an inflammatory response. Sometimes you can eat too much, get a little swelling, your tummy can hurt there too. Sometimes the tummy is going to transfer to other areas though, so we can create referred pain. And depending on the internal organ, which is color-coded here, depending on where we had the pain, that's going to determine which parts of the body we transfer that to. Because there's overlap. There's overlap between our noxious sensory systems and our visceral sensory systems. At the spinal cord, as this cartoon shows, but also in the thalamus as well, there's overlap. So by the time it gets to the cortex, we can't tell. Is it my left shoulder here, or is it my heart? We don't know, because they're going to hit the same target areas in the cortex. So when you have a heart attack, for example, well, this can cause other areas to feel pain, even though there's really nothing going on there. But because of the convergence in the spinal cord or in the thalamus, by the time it makes it to the cortex, we feel that pain elsewhere. Sometimes we'll feel the pain elsewhere if we have very pronounced noxious stimulation, where the pro-inflammatory cytokines actually just diffuse away and directly stimulate nociceptive afferents. Think of this as a really, really bad tummy ache, where the inflammation spreads from your viscera to the somatic tissues. So you can have viscerosomatic pain. Same thing. An area of your body is going to hurt because of visceral pain. This could be because your afferents overlap, or it could be because of very pronounced irritation that directly stimulates those noxious afferents. But without any sensory input, we would have no reflex. The only reason a tendon tap causes muscle contraction is because we have spindle afferents. The only reason that a change in blood pressure can lead to a compensatory change in blood pressure, for example, is because we have visceral afferents, always sensing our blood pressure. Do we have any questions on this before we move ahead? Okay, well then let's talk about these and we'll move on. We're going to start with Adam. What do you want to cover? Sympathetic or parasympathetic?
We can each start with sympathetic.
Okay, I'll have you tell me about the preganglionic neurons there. What's their location?
They are located in the thoracic and lumbar region.
Yeah. Excellent. And maybe lateral horns or something. What neurotransmitter do they release?
They release ACH, acetylcholine.
Fantastic. And what receptor does that act on?
Sympathetic chain ganglion,
Fantastic.
or the post ganglion.
Which which acetylcholine receptor? I'll tell you as fast as I on it. Fantastic. Nicotinic acetylcholine receptors. These are cation channels. All right. That sounds pretty good. Let's go on to the parasympathetic branch then. Alex, where are those found? Preganglionic.
Yeah. Spinal cord.
Okay, that's true. Starts with an S. Spinal cord.
S2 to 4.
Fantastic. Yeah, down there in the sacral spinal cord. They're down in the lateral horns. Anywhere else?
The brainstem as well.
Excellent. And so these are going to form our cranial nerves. Correct me if I'm wrong here. 3, 9, 10. 3, 7, 9, 10. Jeez.
Yep.
Thank you. What neurotransmitter are we releasing, Alex?
ACH as well.
Oh, wow. What receptor? I'll tell you it's fast ionic. If that helps.
Nicotinic ACH as well.
You got it. They have a lot in common. They're located in different areas, and so they're going to innervate different targets. But they release the same neurotransmitter. And they act on the same receptors. They're going to cause fast depolarization in our postganglionic neurons. Sydney, where are those located? Kate, sympathetic or parasympathetic?
We can use sympathetic.
Okay, we're on the postganglionic neuron now. Where do we find those?
So they're usually close to the spinal cord, like the sympathetic chain ganglia.
Nice.
Some can be further out.
Okay, what do we call those?
I don't know. Okay, I'll do it. Give me a look. I'm sorry.
It might be bolded.
It might be bolded. Okay. The ganglia, the paravertebral, the prevertebral. Yeah, you got it. Okay.
So either really close to the spinal cord or not, but usually really close to the spinal cord. That's the idea you should have in your head here. For the generalization for sympathetic postganglionic neurons, they're almost always close to the spinal cord in that paired sympathetic chain ganglia or the paravertebral ganglia. Same thing. They could also be in the unpaired prevertebral ganglia. What neurotransmitter are we releasing?
Norepinephrine
Fantastic.
or ACH.
Oh God, we have to bring that up. Who
I
told you
know.
that crap?
You,
Okay.
unfortunately.
But everything else. So we should really be thinking norepinephrine whenever we're thinking about postganglionic sympathetic neurons. Just like we should also be thinking paravertebral ganglia. What about the receptors? What are we going to act on there?
I feel like you can act on anything.
Okay.
Yeah. Reaction.
Beta is all pretty much the same. Something like that. The devil's in the details. Alpha 1, GQ, alpha 2, GI, beta, GS, something like that. Check my notes, make sure I'm not lying to you. These are things that I just write down and look up. You can't remember all this nonsense. But you can write it down. And because of that, I can't ask you about it. I know. We'll get into the details down below here. First, let's fill in our postganglionic information. Oh yeah. I'm gonna say who? Arlen.
Alright.
So where are we located?
For postganglionic parasympathetic, we are, they begin near the target tissue.
Fantastic. So these ganglia are going to be nearby or actually on the target. So not close to the spinal cord. What kind of neurotransmitter are we releasing?
We're gonna use acetylcholine.
Fantastic. What kind of receptors?
So we are gonna use, there's M2 and M3.
Okay.
M2, they are GI
Fantastic.
at the heart, so they will decrease your heart rate. And then the M3 is GQ, and that's for the GI tract, so that makes your digestion happen.
All right, you're forging ahead. We're down here now. Arlen's already started filling in the details. By knowing the receptor and the coupling underneath, and of course the tissue we're talking about, you'll know what's going to happen. Now all we have to do is fill this in. The receptors that our sympathetic neurons are going to act on, and what they do to our heart and GI tracts. Britta.
Okay.
What are we dealing with here?
The beta
Sweet.
adrenergic receptor?
Yeah. And we've already listed up here that's GS. So what's the effect on heart rate?
It'll increase the heart rate.
Excellent. Increase heart rate. How about the GI tract?
So that's beta and also alpha 2.
Okay, all right. Alpha 2 at our parasympathetic terminals.
And this will also decrease. It will like relax your smooth muscles.
Yeah,
so
there you go.
Decrease
You got it.
digestion.
So we stimulate or we inhibit. The sympathetic and the parasympathetic do opposite things. If we're stimulating with sympathetic, we're going to inhibit with parasympathetic, and vice versa. Any questions on this before we move ahead?
Can we go back to the ganglionic portion of the top just for a second?
Yeah, sure.
So send you a copy.
I'll do you one better. Here you go.
Oh, thank you.
It's all yours.
Thank you.
Yes.
So if you have any questions on this, Harlan is your man. Okay, well, let's talk about some actual effects. The autonomic nervous system is going to help control the non-skeletal muscles throughout our body. We've already touched on the heart. We'll touch on it again. I think it's a fairly important organ. Secondary to the brain, of course. And then we'll finish by talking about the McGrishin reflex and the innervation of the genitals. Finally, talking a bit about spinal cord injury and how this will affect the autonomic functions. All right. Well, nerves aren't the only things that generate action potentials. Muscles generate them too. There are pacemaker cells throughout different organs, for example, in the heart, that are going to generate action potentials to stimulate that cardiac muscle and cause rhythmic constriction. The action potentials here are a little bit different because they are created by voltage-gated calcium channels. We still have voltage-gated potassium channels to cause the repolarization. But we get steady pacemaking because of HCN channels. Those are hyperpolarization activated, cyclic nucleotide gated cation channels, HCN. Yes. Yes. I'm telling you. Yes. Without these, you don't have a pulse. So yes, HCN. Hyperpolarization. That's not so tough, is it? When does hyperpolarization happen? Yeah, whenever we end our action potential, we're hyperpolarized. That activates them. That's the H. Hyperpolarization activated. Make sense? Now for the second part. Cyclic nucleotide. Just go ahead and say it with me. Cyclic nucleotide. Thank you, no one. All right, that's going to be a detail. Cyclic nucleotides. Have we heard of these before? Yes? Yeah. Cyclic AMP, which is what we make whenever we stimulate a GS-coupled receptor. Do we have any GS-coupled receptors at the heart? Holy shit. It's like I planned this. Yeah, we do. So this slope here is where we have our variability. Once we hit threshold, we're off to the races. Our potassium channels are a little slow, so we'll get depolarization, and hyperpolarization no matter what. What varies is this rate of of excitation here, this depolarization to help us hit threshold. That hyperpolarization is going to always activate HCN channels. The question is, how much conductance do they have? And that depends on the level of cyclic nucleotides, hence the CN portion of this. H, because we just hyperpolarized from the previous action potential. This way we pacemake. So one action potential produces the next. CN, so that our input, either through beta adrenergic receptors or muscarinic acetylcholine receptors that increase or decrease cyclic AMP levels, increase or decrease this slope to affect the rate of pacemaking. Not so tough. Just learn what those three letters mean, and you've got this. So this is what's going to drive contraction of the heart, pacemaking at the sinoatrial node. The rate of pacemaking there depends on the amount of cyclic nucleotide, namely cyclic AMP, that is floating around. If we receive sympathetic input, cyclic AMP levels rise, our HCN channels have greater conductance, and this slope increases. So we hit threshold sooner, and we have a higher rate of pacemaking. You can see that right here. Stimulate your beta adrenergic receptors. Notice the difference in the rate of action potentials. Much faster, and that's because we're increasing conductance through our HCN channels. So we get steady pacemaking, but at a faster rate. Depolarization and repolarization driven by calcium and potassium, same. What difference is the latency between these spikes? The beta adrenergic receptors are also going to stimulate the heart muscle. Cardiac muscle is going to contract more forcefully because protein kinase A will increase the open probability of our ryanodine receptors. In other words, more calcium. More calcium coming out, stronger contraction. And then we alter the blood flow. Here we're dealing with smooth muscle. Keep that in mind. The arterioles are going to have our beta adrenergic receptors, which are GS. The larger arteries on the outside are going to have alpha 1, which is GQ. This is going to stimulate. So here's the internal workings of the smooth muscle. This is why GS causes relaxation. When we activate our GS-coupled receptors, increase cyclic AMP levels, that stimulates protein kinase A, which inhibits myosin light chain kinase. Whether myosin interacts with actin or not in smooth muscle depends on whether it's phosphorylated. That phosphorylation is carried out by myosin light chain kinase. Calcium, which is of course stimulated by GQ receptors, that activates kinases that stimulate myosin light chain kinase. If we activate myosin light chain kinase, more contraction. So our smooth muscles in the vasculature will contract and we will get constriction. If it's GS, cyclic AMP via protein kinase A will inhibit this kinase, preventing phosphorylation and thus biasing us toward relaxation. So this will dilate. So we have our alpha 1 out here in the larger external arteries there at the heart, but those perforating arterioles, which are a little bit smaller but head into the muscle tissue itself, are going to dilate. So we'll constrict out here, increasing pressure to drive blood into here, where we've dilated a bit to decrease that pressure and allow perfusion into the heart. So the heart muscle that's working harder is receiving greater blood supply as a result through constriction out here, dilation in here. Same neurotransmitter, but different receptors, therefore different function. So sympathetic input is going to be acting all throughout the heart at the level of pacemaking, strength of contraction, and the movement of blood. We're going to increase perfusion of the heart muscle by constricting those external arteries while dilating the internal arterioles. And we'll do that with just one neurotransmitter, but different receptors. The parasympathetic input is really only going to act at the sinoatrial node. This is the only place where you find the parasympathetic terminals. These are GI coupled. So what happens to the level of cyclic AMP whenever we stimulate them? It goes down. Exactly. So the rate of pacemaking is going to decrease as a result. So now all we're doing is adjusting this slope again, but we're turning it downward because the conductance through the HCN channels, which I highlighted green here, they decrease. Lower cyclic AMP levels, less conductance through the HCN channels, and slower depolarization to hit threshold. As a result, slower pacemaking. So both of these will act together to control the activity of the heart. When we need an increase in cardiac output, sympathetic innervation will accomplish that. When we need to decrease cardiac output, parasympathetic activation will do that. These parasympathetic fibers are going to inhibit the sympathetic fibers as well. So we're going to apply the brakes and let off the gas. Even though we don't actually innervate the muscle or the vasculature directly, by inhibiting the sympathetic innervation of those components, we inhibit them indirectly. Down there in the bladder, we're going to also have paired input from the sympathetic and parasympathetic branches of the autonomic nervous system, and they're going to work together to control urination along with some descending conscious input as well. So here's where autonomic and somatic nervous systems are going to meet up. Presumably, you have the ability to control when you urinate. The reason that you have control of that is because of somatic afferents that innervate striated muscle. So the external sphincter there is going to be innervated via the pudendal nerve. It's going to arise from sacral regions of the spinal cord. We call it onus nucleus. And these are going to control, ultimately, whether or not any urine escapes. So this is the last stop down there, the external sphincter. We have conscious control over this. This is innervated, of course, via nicotinic acetylcholine receptors because we're not dealing with autonomic function. This is the somatic nervous system. So we have fast control over this muscle and conscious control over it. Everything else is more reflexive control. This is going to be autonomic innervation. At rest, we have sympathetic tone that keeps our bladder relaxed and the urethral sphincter, or the internal sphincter, constricted. Same neurotransmitter, of course, but different receptors. And if you know the receptor, then you know what it's going to do. At this internal sphincter, we have alpha-1 adrenergic receptors. That coupling is GQ. GQ is going to be excitatory regardless of the type of muscle. At the bladder, the detrusor muscle is going to have beta adrenergic receptors. These are GS coupled. No surprise there, that's going to inhibit smooth muscle. So our bladder is relaxed. Both of our sphincters are constricted. No urination going on here. And to make sure our bladder tone is kept low, we're also inhibiting parasympathetic output. We will be activating this parasympathetic output as our bladder fills. So let's have a look here. Conscious control, I've made purple here. So here's the last stop. That conscious control from the cortex, we can decide whether or not we allow urination to occur. There is sympathetic tone, that's the red here. It's innervating the pelvic ganglion here to inhibit the postsynaptic parasympathetic neurons. It's also innervating the bladder and internal sphincter to cause relaxation and constriction respectively. As our bladder fills, it's going to stretch. Stretch receptors will sense that stretch and alter this circuitry here. That stretch is going to be picked up as sort of unpleasant. There will be some local synapses within the spinal cord. We'll activate our anterolateral pathway. Well, this is going to have a bunch of stops within the brainstem. One of those areas would be the pontine micturition center, and that's exactly what it sounds like. It's a center or an area in the pons that deals with urination. This controls the autonomic circuitry. Normally this is inhibited by the cortex. When we don't want to urinate, we keep the pontine micturition center inhibited. When it's activated, what it's going to do is inhibit the sympathetic output and the somatic output while stimulating parasympathetic output. So once we've made the decision to urinate, we're going to open up our external sphincter, and then we have a second reflex here that's going to take off. So the stretch of the bladder increases the drive to urinate. It's going to provide some noxious input to the cortex. It doesn't feel pleasant. It's going to provide input to the pontine micturition center to start inhibiting the sympathetic output. So we're not relaxing as much. We're not constricting quite as much. And we're going to start activating our parasympathetic output. Once we've made the decision and the urine is flowing, that's going to stimulate afferents on the urethra itself. Only when there's flow, though. These are rapid adapting, so it needs constant movement through the urethra to drive excitation of the parasympathetic innervation. Once we stimulate the preganglionic parasympathetic neuron, it of course activates the postganglionic neuron via nicotinic acetylcholine receptors, and then we stimulate bladder contraction via M3 muscarinic acetylcholine receptors. GQ, calcium, always excitatory, so the detrusor muscle contracts, we force out the urine until the flow stops. While the flow is going, it's very difficult to stop urination because of this reflex. You can do it, you still have innervation of onus nucleus, and you can clamp this off, but boy is it difficult. Much better to let it just finish, assuming there's a toilet nearby. Once completed, no more stretch of the bladder. No more input here to cause that unpleasant feeling. No more drive to the pontine micturition center. No more inhibition of that sympathetic tone. No more stimulation of our parasympathetic output, because not only do we have no stretch, no more flow, so we're right back where we started. Just sympathetic tone, keeping our bladder relaxed and our urethra constricted. As we fill, we're shifting toward parasympathetic. We go into full overdrive once we allow that urination to occur. Remember, we have the ultimate decision here. We can consciously control this. Very much nearby, we have the genitals, which are also innervated by the autonomic nervous system here. Rather than having the parasympathetic nervous system finish the job. Here, the parasympathetic nervous system is going to get things kicked off. Parasympathetic input is going to cause vasodilation of the pudendal artery. Whenever we have vasodilation of the pudendal artery, blood engorges the genitals, we get some swelling, and we're off to the races. This is going to act on the epithelial cells via M1 muscarinic receptors. Those are GQ coupled. We have nitric oxide release. This relaxes the smooth muscle, and that's why we have vasodilation. The emission arises from sympathetic activation. This is going to, of course, cause the release of norepinephrine. It's going to act on a few different receptors. We have our beta adrenergic receptors still there at the detrusor, so we're going to have relaxation. We don't want any inadvertent urination going on here. We're going to stimulate the emission here by stimulating smooth muscle all throughout the genital tract there. So these are all GQ coupled. GQ is going to be exciting. What could be more exciting than this? So we're going to stimulate the release of and movement of semen. And the actual ejaculation is going to come back to the somatic nervous system there. So here there's going to be stimulation of the pudendal nerve where we get conscious contraction and forceful emission. I'm going to avoid jokes here. Keep my job. Last year R. Kelly came up, but he won't again. He's in the news now. So we have a few reflexes that are going to help control the viscera. And there's some interplay between skeletal muscle, smooth muscle. What happens to tendon reflexes whenever we have upper motor neuron lesions? Hyperreflexia, exactly. Those spinal pattern generators are left uncontrolled. You should think of that as also happening to the autonomic reflexes as well. We have hyperreflexia of our autonomic nervous system. So after spinal cord injury, not only is there a change to somatic or conscious output, but there's also a change with autonomic output, where these reflexes act in an uncontrolled manner, which can lead to dangerous increases in blood pressure, particularly whenever we have higher spinal cord lesions that are above about T6 or so, which leaves the splanchnic nerves intact. Now these are going to innervate the GI tract. They're going to play a big role in regulating our systemic blood pressure because of the amount of vasculature that they innervate. So they're going to hit about 25% or so of cardiac output. They'll be able to control that. We send a lot of blood to the gut. And the uncontrolled activation of our sympathetic output can lead to dangerous increases in blood pressure by causing constriction of those blood vessels. Hopefully you remember, sympathetic is not rest and digest, it's fight or flight, so we're not moving blood to our gut. We're going to constrict those blood vessels. We're going to also increase blood pressure whenever we have sympathetic activation. Normally this is kept under control. We have additional sensors of blood pressure throughout the body. They're going to innervate the brainstem nuclei for parasympathetic neurons. This is going to keep us at a fairly constant blood pressure throughout the day. Whenever we have a spinal cord lesion and that descending input is lost, then the reflexes can take over. Now, sympathetic neurons can be activated by noxious stimuli. I think I brought that up at the beginning of the talk. If there's something that's hurting you, you probably need to respond to it, fight or flight. Noxious input can arise from fairly benign events like the filling of the bladder, which you might not be so aware of if you have a spinal cord injury. The ascending input can be severed, so you're not aware that your bladder is full. But that lower portion of your spinal cord that's still connected to those ascending noxious afferents are still well aware of that. And that can lead to activation of the sympathetic nervous system without proper descending control. So we get inadvertent and uncontrolled vasoconstriction in the GI tract, which can dramatically drive up our blood pressure. This is the highest reading I've found for autonomic dysreflexia. Fairly high. This is the systolic blood pressure. This can be a big problem. So this is an emergency. There are many things that can lead to activation of sympathetic output. So this is something that has to be monitored. Anytime you have those high spinal cord lesions, this is an issue. Once it's below that and you have some intact ascending control, inhibit that sympathetic output, not so bad. It also severs the ascending input from the bladder, for example. So the lower spinal cord lesions won't necessarily create autonomic dysreflexia. There are some instances of it occurring within the lower thoracic spinal cord, but they're rare. Almost always it's going to be a higher thoracic lesion. When you go below that, you can start to have different effects on the bladder once you start to enter the sacral region. Any spinal cord injury, of course, can affect the bladder. That descending input from the pons, for example, that controls the micturition reflex gets severed when you have a spinal cord injury. So the reticulospinal tract, when that's severed, input from the pons down to the micturition reflex centers are lost. And you can create a couple different types of neurogenic bladder as a result. It depends on the level. If it's above the sacral spinal cord, then we have our parasympathetic input still in place. So this reflex becomes hyperactive. That stretch, any little stretch on the bladder is going to stimulate contraction. We have hyperreflexia when we leave our parasympathetic preganglionic neurons intact. So you tend to see spastic bladder, where there's uncontrolled contractions and they're not timed up with any relief of the sympathetic tone. So the sphincter, the internal sphincter, remains contracted, but you get forceful contraction of the bladder, which can create extreme pain. There can also be, of course, involuntary urination as a result as well. If we have damage to the preganglionic parasympathetic neurons, of course, this would be more like a lower motor neuron lesion, where we have hyporeflexia as a result. So now we have a loss of contraction, the inability to forcefully contract the detrusor. So we get overflow, incontinence, an acontractile bladder, and the need for catheterization. This is only whenever we have lower sacral spinal cord damage. Anything above that, where we're just lesioning the connection with the Ponti micturition center and back, then we're going to have a spastic bladder. So, upper motor neuron lesion, lower motor neuron lesion, if you like to think of it that way. Any questions? All right, let's go through these, and that'll be it. Okay, this first question is about pacemaking at the heart. Lauren, tell me about pacemaking at the heart.
Okay, so parasympathetic decreases excitability into the glucose receptors.
Okay.
Or GI couples.
All right, so we activate an M2 muscarinic acetylcholine receptor. They're GI coupled. So what?
So the release of acetylcholine inhibits adrenal cyclase and reduces the excitability of the heart.
Okay, great. Nice. We're going to reduce excitability, and it has something to do with inhibiting adenylyl cyclase. Can we fill in the blank between inhibiting adenylyl cyclase and slowing this, slowing our pacemaking?
Cyclic AMP.
Great. Cyclic AMP. Well, what does that act on?
The HCN.
HCN. Well, what does that mean?
Oh
Oh, okay, the H is hyperpolarization. We'll see if this makes sense. Cyclic nucleotide gated cation channels. That's why we call them HCN channels. But you need to know what the HCN means so that all this makes sense. H, hyperpolarization. Why would we want a cation channel activated by hyperpolarization?
That way you're not activating for it, so it can actually repolarize properly.
Okay, great. So we allow for repolarization, we allow for hyperpolarization. And when do we hyperpolarize? What happens to drive hyperpolarization?
Activation of those potassium channels.
Yeah, exactly. Yeah. The action potential drives another action potential because that hyperpolarization increases our conductance for cations. So we're going to depolarize. We're going to hit threshold and we're going to drive another action potential. And then we're going to activate HCN again. And we'll drive another action potential. And we'll activate HCN again. And we will continue to live. This is variable. The blue portion here, that rise back to threshold. So, Lauren has already told us when we have parasympathetic input, we're going to activate our M2 muscarinic acetylcholine receptors. They are GI coupled. They inhibit adenylyl cyclase. The reaction that this enzyme catalyzes is the production of cyclic AMP. If we inhibit the enzyme that makes cyclic AMP, of course, cyclic AMP levels drop. So what happens to this slope?
Less aggressive.
Yeah, it kind of evens out, right? We're gonna reduce the slope. And as a result, the pacemaking that occurs is going to be slower. All this stuff is still going to be the same, but what differs is that rate of rise. So that we're firing action potentials less frequently, and we have a slower heart rate. That's if we activate a GI coupled receptor. What about sympathetic input? The opposite, exactly, yeah. So whenever we have input from the sympathetic fibers, what sort of receptors do they act on? Yeah, beta-adrenergic receptors. They're GS coupled. They stimulate adenylyl cyclase, cyclic AMP levels increase, and this slope, instead of flattening, sharpens. So we have a faster rate of pacemaking. Something kind of like that, you get the point. So we'll either increase the rate by increasing cyclic nucleotide levels, or we'll decrease the rate of repolarization hitting threshold because we'll reduce HCN conductance. Okay. Well, let's move on and talk about the nutrition reflex. Once we start urinating, it goes to completion.
Yeah, on that last one, I was asking about norepinephrine.
Yeah.
Is that just working on the bars?
Yeah.
Okay.
Yeah, here at the node. Yeah, beta-adrenergic receptors, GS coupled, increase cyclic AMP, increase conductance of HCN channels, so after we hyperpolarize, we will more readily reach threshold. If that's sooner, we'll fire the next action potential sooner, we're going to contract the heart sooner, heart rate increases. I don't know if I can draw this again in time. So someone's just gonna walk me through my cartoon I've made for you. Okay, Ashley. Bladder is empty. Why aren't I urinating?
The PMC is inhibiting any sort of parasympathetic output. So the sympathetic nervous system is going to be causing the bladder to relax.
Okay, great. We have sympathetic tone. Tell me about that sympathetic tone. Why is the bladder relaxed?
Through the beta adrenergic receptors.
Yeah, what's their coupling?
GS.
Yeah, this is smooth muscle. So what does GS do?
It's going to relax the surface.
Fantastic. Bladder's relaxed. How about this?
That's the internal sphincter.
Excellent. And what receptor are we acting on there?
The alpha-1 adrenergic receptors.
What's the coupling on that one?
They are GP.
Excellent. Always excitatory? Yeah. So we constrict. So we're relaxed and constricted. Both of those. We're not squeezing any urine out and we're not allowing any to leak out. And we have conscious control as well. Now you mentioned the PMC, but is there anything else that we might have control over? In purple.
The onus nucleus.
Fantastic. So we have our cortical spinal tract coming down. We're going to innervate lower motor neurons down there in the sacral spinal cord, and they innervate, what is this?
The external sphincter.
Fantastic.
Yeah. Which just controls the voluntary release of whatever's in the body.
Which receptors?
Nicotinic, axia.
But of course,
whatever.
yeah, exactly.
You see it.
Striated muscle. We have fast control over this. And we have conscious control over it. Eventually we do get the urge. Brianne, what gives us the urge to urinate? What's kicking this whole thing off? As my bladder fills, because I keep drinking water, I just feel like dancing. Why? Does the stimulation of visceral afferents create a pleasant feeling? No. Exactly. No, they don't. Do we have any visceral afferents here that you can see? Excellent. How can they possibly sense a stretch of the bladder?
From the detrusor muscle.
Mm-hmm. And they have stretch receptors.
Mm-hmm.
So when the bladder stretches, the nerve gets stretched, that pulls open ion channels, and it starts firing action potentials. And it doesn't feel good. Okay. Okay, so that's the kind of unpleasant feeling that we get when our bladder fills. This way we want to go do something about it. If it felt good, we might just sit there and dance all day. That could be bad. We might get backflow. We don't want that. So, activation of this detrusor afferent here. What does that do?
So-
Besides make us want to dance.
So it,
Daniel, would you like to help us out?
Well, it looks like that orange arrow is traveling to the spinal cord,
True.
and then it's gonna hit up that pontine micturition center.
Okay, great. We're going to synapse down here. We'll send up there. We'll send up there. Oh, what are we doing here?
It's gonna inhibit sympathetic.
So we start to recruit our pontine micturition center. So up there in the brainstem, that would be your spino-reticular tract. So it's like one of those offshoots of the anterolateral pathway. That starts to inhibit the sympathetic output. Oh. How does that affect the bladder?
That'll make it so will want to contract the detrusor muscle to begin expelling urine and
Great.
open up that internal sphincter.
Yeah, we're taking off the brakes here. Taking off, I don't know, the gas, I suppose.
Right.
So we're not constricting as much, we're not relaxing as much. Anything else going on?
It'll start to inhibit onus nucleus so that we will want to open up the external sphincter.
Yeah,
to
it
allow
gets hard to have conscious control at some point.
Yeah.
Yeah.
Not allowing me out.
Yeah. Ultimate control is up here though. So let's let it go. Why does this go all the way to completion? Caleb. Urine is, oh my God. A little different there. Urine is flowing. Now what? What keeps this whole thing going until we're done? How do we know when we're done? What's that?
The brown one.
Oh, the brown one. Yeah. Ran out of colors here. What's this brown one sensing?
The flow of urine.
The flow. Does it have to keep flowing? To keep stimulating it? Yeah, exactly. These will rapidly adapt. We need a constant source of stimulation there. So as long as urine is flowing, we're going to keep activating. What the hell is this? What is this green thing that I've drawn there? No. Parasympathetic, exactly. We're going to keep driving parasympathetic output. Now what does the parasympathetic output do here? Don't tell me it activates this. I can see that. What is it doing at the bladder? Oh, how does it do that?
Stimulation of the acetylcholine receptors.
And their coupling is?
GI. GQ.
There we go. There we go. Yeah. And that's it. Once it's done, no more stimulation here, no more stretch here. Our sort of basal sympathetic output resumes, and presumably we stop trying to urinate. This closes, and we're back to where we started. We're out of time. We're going to stop here. If you have any questions, come by and see me. I'll see you Thursday.